Welcome back to another unit test walkthrough. Today we're going to go over the logs and exponential version 2.4 unit test. I am known to give very hard questions on logs and exponential functions, and this is no exception. Let's get started with the first standard, properties of logarithms and indices. Out of the three standards, this is probably the easiest one. Question 1. We would like to express everything in terms of A. Part A. 8 to the 2x plus 1. So that means 8 to the 2x plus 1 is equal to 8 times 8 to the 2x. 8 to the 2x, that's 8 to the x squared. Therefore, we have 8a squared. Part B. 3 times 1 over 2 to the x. 1 over 2, that's 2 to the negative 1. 2 is 8 to the 1/3. Thus, our final answer is 3 times a to the negative 1/3. Question 2. We would like to express in terms of log base 2 of 3 and log base 2 of 5. This kind of question is very common on exams. Part A. Log base 2 of 60. We have the same base, so no need to worry about it. We just need to decompose 60 into multiples of 3 and 5. 60 is 4 times 15, so we can express it as 2 times 2 times 3 times 5. Going back to your prime factorization. Therefore, this log base 2 of 4 plus log base 2 of 3 plus log base 2 of 5. This guy is equal to 2, that guy is A, that guy is B, and we're done. Second part, log base root 3 of 15. Both A and B are log base 2. So right off the bat, we know that we have to change the base. Log base 2 of 15, that's log base 2 of 3 plus log base 2 of 5. You can even read off the answer from the previous part, if you wish. Log base 2 of root 3. Root 3, that's 3 to the power a half. So, using the power law, we can rewrite this as 1 by 2 log base 2 of 3. Therefore, we have A plus B divided by a half of A. Or in other words, 2A plus 2B divided by A. Question 3. Part A. For A, B greater than 1 and C greater than 0, prove that log base A of B is greater than log base A plus C of B. Easy peasy. So, we are given that A, because A and C are positive, A plus C is greater than A. Therefore, log base A plus C is greater than log base A. Therefore, and it's also positive. Therefore, 1 divided by log base A plus C is less than 1 divided by log base A. Multiply everything with log of B because it is positive. then notice that this is nothing more than the change of base. We obtain our final answer. Part B. We would like to prove that log base A of B is greater or equal to log base A plus C of B plus C. Let's use the hint. It's there for a reason. So let's say, let's consider log base A of B minus 1 minus log base A plus C of B plus C minus 1. The reason we want to do this is that depending on the sign of this inequality, we can deduce the final answer. Log base A of B minus 1, that's log base A of B divided by A. Log base A plus C of B plus C minus 1, that is log base A plus C of B plus C divided by A plus C. Because B is greater or equal to A, B divided by A is greater or equal to 1. Because of that, B plus C divided by A plus C has to be less than B plus A. If you're not sure, just plug in some random numbers. If B is 3 and A is 2, 3 plus 1, that's 4. 2 plus 1, that's 3. 4 by 3 is less than 3 by 2. Therefore, we can continue our line of reasoning up here. This is, therefore, log of A plus C of B plus C divided by A plus C is less than log of A plus C of B divided by A. Therefore, the original expression is greater than log base A of B by A minus log A plus C of B divided by A. And using part A, we can deduce that this is greater than 0 because we have a greater base with the same argument. Part C. We are now asked to prove that 3 halves log base 3 of 29 is less than log base 2 of 28. Why don't we consider the difference of the two? And depending on the sign of this expression, we can then deduce the inequality. And if we factor the 3 out, then change of base, it should be a 9. If this is A and that is B, this is A plus 1, this is B plus 1. And from part B, we showed that log base A of B is greater than log base A plus C of B plus C. Therefore, this guy has to be less than 0. Therefore, we have our final answer. Question 4. we have the left-hand side. We'd like to show that it is equal to the right-hand side. Log base a of n and log base ab of n. I would like to change of base first, because notice that we have all the n's in common. So we can express this as 1 divided by log base n of a divided by 1 divided by log base n of ab. This now gives us log base n of ab divided by log base n of a. Now we have the same base. We can use the change of base formula again. This will now give us log base a of ab, or log base a of a plus log base a of b, or 1 plus log base a of b as requested. Question 5. When you see such an intimidating expression, do not fret. Tackle it one part at a time. You will get the marks for the parts that you are able to solve. Let's start with the left-hand side. Log base 7 of 175 minus log base minus 1 divided by log base 7 of 10. This is a classic strategy. You can always rewrite 1 as log base 7 of 7. This will then give us log base 7 of 25 divided by log base 7 of 10, or log base 10 of 25. Let's look at the second term, as this one is more intimidating. Log base 4 of 3, log base 6 of 5, log base 2 of 7, okay, log base 10 of 9. Down here we have 3 times log base 3 of 2, log base 2 of 3, log base 4 of 5, log base 6 of 7, and log base 8 of 9. Honestly, this looks very annoying, if I'm being honest. So what I am gonna do is I'm gonna put all of them into the denominator. I'm gonna keep a 2 up there. Log base 4 of 3, that's 1 divided by log base 3 of 4. Log base 6 of 5, that's 1 over log base 5 of 6. Log base 2 of 7, that's 1 over log base 7 of 2. And lastly, log base 10 of 9, that is, log base 8 of 9. Log base 10 of 9, that's 1 over log base 9 of 10. And the reason I'm doing this is because they start canceling out very nicely. Log base 2 of 3 times log base 3 of 4 times log base 4 of 5 times log base 5 of 6 times log base 6 of 7. All of that is log base 2 of 7 times log base 2 7 of 2. This guy is convenient. I love it. And we're left with log base 8 of 9 and log base 9 of 10. We're almost there. Let's finish it off. We have log base 10 of 25 for the first term. We are going to add two logarithms, so we would like them to have the same base. So instead of putting it here, I'm going to bring it up. Use the power law. Et voila. We have log base 10 of 25. We have log base 10 of 4. Therefore, the left-hand side is equal to log base 10 of 25 plus log base 10 of 4. That is log base 10 of 100, or 2. Very nice. That now gives us a target to tackle the right-hand side. Right-hand side. If anything, I think this one is more straightforward. You just have to deal with a lot of algebra, but that's pretty much it. Okay. So let's change the base for the last one to make it log base x minus 1. That'll be 3 times log base x minus 1 of this guy divided by log base x minus 1 of x minus 1 cubed. This guy will give 3. They will cancel out. So you're left with log base x minus 1 of the product of all of them. And all you have to do now is factorizing and bring it home. Gone, 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 gone. Et voila. We just successfully showed that the right-hand side is equal to the left-hand side. N of standard. Moving on to standard 2, logarithmic and exponential equations. Part A. I usually love starting this section with a relatively straightforward question. You don't even need to take logarithms here, because 81, that's 3 to the 4. Therefore, you just have to equate the exponents. X minus 1 to x minus 2 to x minus 1 is equal to 0. So x is either a half or 2. Part B. 4 to the 3x plus 2 is 8 times 8 to the x plus 3. What are we going to do here? 4 to the 3x plus 2. And let's break it down. This term is equal to 4 squared times 4 to the 3x. 4 to the 3x, that's actually 8 to the 2x. So you may have noticed that we have a hidden quadratic equation here. So if we let t equal to 8 to the x, the equation becomes this. Minus 8t minus 3 is equal to 0. This is a good old humble quadratic equation. So we're gonna subtract 12 plus 4, and we are at 4t plus 1 times 4t minus 3 is equal to 0. T is negative 1 by 4, or t is equal to 3 by 4. T is 8 to the x, and 8 to the x cannot be negative. If 8 to the x is equal to 3 quarters, then x is equal to log base 8 of 3 by 4. This is a perfectly valid answer. If you want to simplify your answer even further, you may do so. But unless prompted by the question, you can keep your answer like this. It is perfectly fine. Part C. When dealing with logarithms, please be very careful with the domain. If you're like me, you would write down the domain or the restrictions before solving the equation. So in this case, x has to be greater or equal to -1 for this term to exist, because if this is the case, then this term would exist without problem. The argument of a logarithmic expression must never be negative or zero, at least in the real number system. Okay, so we're adding two logarithms of the same base. So we are going to multiply the arguments. This is basic algebra, so I'm not going to spend a lot of time narrating every single step. If you would like more help, please go back to the video that I walked through the Algebraic Skills unit test, where I explain these in more detail. Links will be added to the description. We found our two values of x. However, going back to our domain, x has to be greater or equal to -1. So we have to reject this, and we can only accept x is equal to 2. Part D. 2 log base 2 of x minus 1 minus log base 2 of x minus 2 is equal to 2. So, domain right off the bat. X has to be greater or equal to 2. Let's manipulate the left-hand side. The first term can be expressed like this. Now we have the difference of two logarithms of the same base, so we divide the arguments. X minus 1 squared divided by x minus 2 is equal to 4. X minus 1 squared is equal to 4x minus 8. So x is equal to 3. Our domain is x greater or equal to 2, so we can accept this without any problem. And we're done with question 1. Question 2. For these kind of questions, I would always look for opportunities to simplify as much as possible. And looking at the second equation, we can simplify it straight away because we recognize that 4a squared minus b squared is nothing more than 2a minus b times 2a plus b. And we have a difference of two logarithms of the same base. So let's start off with the second equation. Log base 3 of 4a squared minus b squared divided by 2a minus b. That now gives is equal to 2. In other words, log base 3 of 2a plus b is equal to 2, or 2a plus b is equal to 9. Going back to the first equation, 2 to the 2a to the b plus 2 is equal to 16 to the 5 plus a. Let's change everything to the same base. 2 to the 2a to the b plus 2, that would be 4 to the a times b plus 2. Changing the right-hand side to base 4. And that gives our second equation. Or AB is equal to 10. Equation 1, equation 2. Now we can solve them simultaneously. If 2a plus b is equal to 9, b is 9 minus 2a. We are going to solve this system of equations using substitution. Multiply both left and the right hand side by -1. Bring it over. Factorize. If a is 5 by 2 and ab is equal to 10, b is equal to 4. If a is equal to 2, ab is equal to 10, b is equal to 5. So our candidates for AB are 5 by 2 and 4, or 2 and 5. Now it is important to check our answers. Go back to the equations. Look at the term log base 3 of 2a minus b. This term only exists if and only if 2a minus b is strictly positive. So if a is equal to 2 and b is equal to 5, you will have a negative argument. Therefore, the only solution that we can accept is 5 by 2 and 4. Not checking your restrictions will cost you at least 1 mark on the exam. And on the unit test, it could literally be the difference between a pass and a fail. Because I need you to know that you need to check the restrictions at all times. Question 3. You're given the domain for x and y. At first glance, this question is very intimidating because it is. You look at this equation and you just want to turn away. But I have carefully scaffolded your way through the question. So let's stick to it step by step and we shall get to the very end. Part A. What will you do? Apart from panicking. This guy looks factorizable. This guy is a perfect square. We might be able to get some head start. If we factorize this guy, we would get y plus 1 times, 1 minus x times y plus 2. The second term is a perfect square. What next? We can use our log laws to simplify the first term a bit more. This guy is simply 1. Now you need to be very careful dealing with the square up here. X minus 1 squared is always positive for all real values of x. As long as it's not equal to 1, you're good to go. However, if we want to take the 2 down, we must make sure that whatever is left in there is also positive. So I'm going to slap the modulus sign on, just in case. I'm going to bring that 2 to the other side. The absolute value of x minus 1 can be x minus 1 or 1 minus x. However, x is less than 1. If x is less than 1, then x minus 1 is less than 0. So when breaking the absolute value sign, you actually get 1 minus x. And therefore, you arrive at the first equation that I asked you to prove. Hence, find the value of this term. Look at the symmetry. Using the change of base formula, you can see that now we have a hidden quadratic equation. If it is not clear to you, let's use a dummy variable. So t plus 1 divided by t is equal to 2. T squared plus 1 is equal to 2t. T minus 1 squared is equal to 0. T is equal to 1. Therefore, log of 1 minus x times y plus 2 has to be equal to 1. So that is the end of part A. In part B, you are asked to solve for simultaneous equations. Notice that the first equation has been taken care of in part A. So we're just going to use the results that we have derived. In other words, this is now our first equation. The second equation remains the same. The first equation is crucial because now we can cast the second equation entirely in terms of x. So this is the first equation. The second equation, y plus 5, that would be 4 minus x. 2 plus y, that's 1 minus x. X plus 4, that's x plus 4. First equation, x plus y is equal to negative 1. Second equation, log of 1 minus x of 4 minus x divided by x plus 4 is equal to 1. X plus y is equal to negative 1. 4 minus x divided by x plus 4 is equal to 1 minus x. X plus y is equal to negative 1. 4 minus x is equal to negative x squared minus 3x plus 4. And now we have a quadratic in the second equation. So x is equal to 0 or x is equal to negative 2. If x is equal to 0, then y is equal to negative 1. If x is equal to negative 2, then y is equal to 1. But y cannot be equal to 1. Sorry, y cannot be equal to negative 1. We cannot accept the first solution. Therefore, the only answer we have is negative 2 and 1. Moving on to standard 3, logarithmic and exponential functions. In this question, we are asked to find the equation of the asymptote to the curve. A logarithmic function has a vertical asymptote. And the vertical asymptote will occur at the point where the argument is equal to 0. So the equation is x is equal to 1 by 3. Part B. The maximal domain of this guy. As we know, the domain of an exponential function is for all real numbers. So therefore, the domain of y is actually the same as the domain of the rational function, which is all real elements of, which is all real numbers except 2 and 4. Part C, find the maximum value of this function. Question 1, is this function increasing or decreasing? Look at the base. The base here is 1 by 3. So we know the function is decreasing. That means that the maximum value will be obtained at the smallest x value. In other words, 8 times 1 by 3 to the negative 2 plus 1, or 24. Part D, find the inverse of the function. To find the inverse, first you have to switch x and y's. Now we want to solve for y. Swap over. And now you just got to write this is equal to 1 by 3 minus 3 to the x plus 1. And that is the end of question 1. Question 2 is a simple compound interest question. You're given the Joe invested 4,500 in an account that compounds biannually, aka twice a year. At the end of the 12 years, the investment doubled in value. So, principal times 1 plus rate divided by 2, y, compounds twice a year. How many times did it get to compound? 24 is equal to 4,500 times 2. Therefore, 1 plus r to the 1 plus r divided by 2 to the 24 is equal to 2. 1 plus r by 2 is 2 to the 1 by 24. R by 2 is 2 to the 1 over 24 minus 1. So r is equal to 2 to the 25 by 24 minus 2. So that's the end of question 2. Question 3. In part A, we're asked to solve the inequality, and in part B, once again, you are asked to solve an abomination of an inequality. So let's start off with part A. We would like to solve this inequality. For this to be true, x squared minus 2x minus 2 has to be greater than 1. Now we're just going to factorize. And that gives us our inequality. However, you also have to pay very close attention to the domain of the function y equals to log base 3 of x squared minus 2x minus 2. This guy is undefined when this part over here is positive. And there are several ways you can go about solving this inequality. But the quickest way would be by completing the square. So, when comparing our inequality solution set with the domain, we deduce that the final answer would be x less than negative 1 or x greater than 3. Moving on to part B. This is where it gets very tricky. Obviously, when you see a question like this, you will try your best to find ways to not deal with every single component here. How do we do that? We just looked at this part in part A. So let's look at log base 4 of x squared plus 4. We know that x squared is greater or equal to 0, so x squared plus 4 is greater or equal to 4. Y equals log base 4 of x is an increasing function. Log base 4 of x squared plus 4 is greater than or equal to log base 4 of 4, or equal to 1, greater than 0. So this part is always positive. Solving this guy equal to 0, that is trivial. We know that this guy cannot be equal to 0. In fact, 2 to the x squared minus 3 is strictly positive. You don't need to prove this, but if you wish, we'll start with the same line, and you'll come to the conclusion that 2 to the x squared minus 3 has to be greater or equal to 2 to the negative 3, or 1 by 8, which is positive. So in essence, this term is positive, that term is positive. This inequality is equivalent to log base 3 of this guy divided by that guy, greater than 0. For the star inequality to be true, either both the numerator and the denominator are positive, or both of them are negative. Sorry, that should be a negative. If you want to be extra careful, you should also include the very last condition, that the argument of a logarithmic expression must be positive. So let's solve the first system. First equation gives us x less than negative 1 or x greater than 3. The second one is basically x minus 2 times x plus 1 greater than 0, or x less than negative 1 or x greater than 2. And now we would like to put everything on the number line. The first one, we have roots at negative 1 and 3. So this is our origin. And we can take that part or that part. The second inequality has roots at negative 1 and 2. And we can also take either ends. The third inequality that was just solved earlier, one of the roots is 1 minus root 3, so a bit less than negative 1. And the second one is 1 plus root 3, so somewhere between 2 and 3. Root 3 is around 1.7, give or take. So the part that satisfies all of the inequalities will be from negative 1 to 3. Sorry, less than negative 1 or greater than 3 when combining all three solution sets. Let's look at the second option. For the first inequality, we would get negative 1 less than x less than 3. So we will take the part in between. For the second inequality, we will get negative 1 less than x less than 2. And for the third part, because the arguments cannot be negative, x is still less than negative 1 minus root 3, or x is greater than 1 plus root 3. So let's look at the parts that they all have in common. First inequality, you can take the middle part. Second inequality, you can also take the middle part. Third inequality, you have to take the parts on the sides. So what values of x do they all have in common? Only the tiny part between negative 1 to 1 minus root 3. That's the only part that they have in common. Therefore, the inequality is true for x less than negative 1, or negative 1 less than x less than 1 minus root 3, or x greater than 3. End of question. Moving on to question 4. In this question, you're first asked to sketch the curve of 1 over 4 to the x minus 2 for x between negative 1 and 3. If x is equal to negative 1, we'll get 64. If x is equal to 3, we'll get 1 by 4. We know that this is a decreasing function. This is not the scale. If x is equal to 0, then you would get 16. And 64 is over here. So the curve would look somewhat like this. But since we're only interested in the parts between negative 1 and 3, we'll start here and we'll stop there. Pay very close attention to the domain. Part B. The graph of that guy undergoes the following transformation. Let's do one transformation at a time. First off, you're translating it 4 units up. Simple enough. Then we reflect it in the y-axis. What does that do? A reflection in the y-axis means that x becomes negative x. Now it undergoes a vertical enlargement with scale factor a. Vertical enlargement factor a. And lastly, a horizontal translation b units to the right. Translation b units to the right. We know that this curve is the same as this curve. So, what can we deduce from this? 1. Let's rewrite this guy in base 4. So that would be a times 4 to the power of x minus b plus 2. Therefore, 2 minus b is equal to 0, or b is equal to 2. A is equal to negative 2. And c is equal to 4a, or equal to negative 8. So this is one possible answer. Bonus points if we can explain why this is not the only solution. And that is the end of the unit test. I hope that you find the test challenging and really stretching your understanding of the topic. If you like the video, please leave a like and comment. And yeah, I'm looking forward to see you guys in the next one. Peace.